let's get started here. First thing I want to talk about is announcing Project 4. This is no longer in preview mode. I think I called it whatever that note I had at the top. This is the project release. The only thing I don't have is AO2 is not 100% defined. I know what it is. I know roughly what it's going to be. I just don't have it typed up. But goodness gracious, nobody's on AO2 yet. I don't think that's going to matter. So the project here is Enemy AI. Let me grab this. I'll grab the code. I'll clone the code. Let me go through the doc a little bit first. I'll fluff up this doc with a little more context too. I like to have my context before each lecture test to tell you why exactly you're doing what you're doing. But I'll also add that right now. So what you're going to build is the AI for a game. And you know what? Let me clone this first. And by the way, just saying up front, Friday's lecture is going to be just examples. So if today we spend too much time talking about this project and we don't get through all the slides today, I'm perfectly fine with that. We'll clean up the slides on Friday, and then move on to examples after that, because it'll be open-ended live coding on Friday and interacting with chat. And you know what? If chat wants to talk about genetic algorithm, that's what we'll end up doing Friday. So let me clone this repo and show you what the starter code is. I won't go through all the code. There is a lot of it. One of my fears here, so hopefully this doesn't happen to you, but one of my fears is that some of you will get overwhelmed by all of the starter code, because there is quite a bit. I'll tell you, don't get overwhelmed. There is a lot of it. To get the... Yeah, look at all this stuff. Ooh, baby. For those of you who are interested, feel free to look through it. Everything here, I only use topics that I cover in 116 or 115, I guess. So you are capable of reading all of this code and understanding what it is based on what I've covered in lecture. There's nothing that should really catch you off guard. Your code is all going to go into this class. This is where you're going to complete all your lecture tasks and application objectives. So if you don't want to explore all of the background, there's not very much that you do absolutely have to understand with the rest of this code. So let's run this and talk about what it is. To run it, run the game server. By the way, this is what took so long getting this out, is getting all the starter code working the way I want it to. Let's set up our Scala SDK. 13.4. Let's run the server. Compiling. When we talk about linked lists, do you make the linked list class? So I give you the linked list class. It's actually in the repo here, this linked list node. And all these methods, you're welcome to use these methods on the linked list node. But the way the lecture tasks, the first 3 lecture tasks are designed, is you're going to have to write algorithms that work with this linked list structure. So we run that, and then we go to the index.html, the web front end. Let's open this in the browser. And 404 not found. Are you sure? Are you sure, IntelliJ? I see students getting this error a lot, actually. That's actually the first time I've gotten that. So I actually have to use the fix, probably because I'm on Windows right now. I don't get that error in Mac. So if you do see that error, I'm glad I got it here because I get to show you the fix. If you open in Explorer and actually go to your file system and then double click it, you'll get rid of that error. So here's the game. All the starter code, most of it is just setting up this game so the game is able to be played. WASD, or the arrows, to move around. And this time, obviously, of course, this looks very much like towers. It borrows a lot of the code for the graphics, at least. The big difference here is that you can shoot, and you can rapid fire even. So these 3 blue circles here are AI characters. I'm going to go, oops, I ran into him, I got bodied and died. When you die, you go back to the spawn point, and you can shoot the AI, and they'll go back to one of their spawn points. The reds are their spawn points. The one big problem with this game is that the AI is completely dumb. The AI right now is just moving around using math.random. There's no rhyme or reason to the way that they behave. They're just strictly randomly moving around. Your task for this project is to add the artificial intelligence into these AI characters, so they will actually attack, they'll actually do things, they'll fire. We want the AI to actually be pretty smart in this game. So to that end, the tasks, first, an AI, to be able to target a player, wants to find the closest player on this board. So we're going to write functionality to find the closest player to a particular AI character. This is going to be done using Euclidean distance, which of course has its problems. If you have this character, the closest one to it is this character. If we're using Euclidean distance, they're trying to just move through these walls. Of course, not great, but that's what we're going to do for LT1. LT2, we're going to take a path that an AI wants to travel and turn that into a vector. Which direction are they going to move? And for both of these, I should mention, we're going to use the linked list node class. We're going to use that linked list node of player locations, where's my IntelliJ? Which a player location is a class defined in the starter code. It's just an XY location and an ID to identify the player that we're referring to, that we're locating. So you have a linked list of player locations. Find the closest player, find this player, use those player IDs, etc. We'll talk about that. We can talk about that after lecture. I can go into more details and everything. And of course, next week's lab will be all about getting set up with all this. Yeah, next week's. So path to direction. Here's a path that I want to follow. Which direction do I go in for an AI character? Computing the path. Okay, we can travel a path, but we don't have paths yet. So let's compute a path. If there's a destination where an AI character wants to go, let's return a path of the tiles that they're going to move through on this grid system to be able to travel from their location to their destination location, which will be the closest player, the location of the closest player. All these methods are combined to build this AI that's going to hunt down the player that's closest to them. Making decisions, this is where we get into trees. We're going to have a tree, a decision tree where the AI is going to choose which action they're going to take. So each node in this tree, well, we haven't talked about trees yet, but each node in this tree can either be a decision to make, a yes or no question, which is going to determine which direction you're going to go in this tree. And then the leaves of the trees, again, terminology we haven't introduced yet, will be the actual actions that can be taken. So this way we can have an AI make choices based on the current state of the game and the locations of all the other players, make a decision about what they're going to do. Finally, we get into a more advanced feature, something we definitely want. What I mentioned was a problem before, is avoiding walls. So if we're just finding the closest player by Euclidean distance and then finding a direct path to them, when we're doing that in LTs 1 and 2, you're not worried about walls at all. You can have a path that just goes right through walls, and then the AI just gets stuck on a wall. Not very interesting. LT 5, 6, and AO1, we're going to fix that. So let's find the distance to a player while avoiding walls, the closest player while avoiding walls. So this mirrors the first few methods that we wrote, but avoiding walls. And then AO1, find a path from an AI character to the closest player while avoiding walls, and have that be the shortest path, the shortest distance traveled to be able to get to that player. AO2 is going to be building a more advanced decision tree. I have a decision tree in the starter code that I give you just so as you're writing these methods, you can actually see stuff happening. By the time you get to LT4, you'll be able to see your AI actually behaving like AI, actually hunting the player and firing at the player. I have a basic decision tree, very simple one in the code. Your AO2 objective is going to be to make a more sophisticated AI that can use all this code, avoid walls, fire only when it's effective, actually aim at players, and get just better AI in the game. Yeah, AO3 is sentient AI. if you build sentient AI in this game, then yeah, you can have all the AOs. And that's Enemy AI. This is the last project that we have for 116 this semester. It exists. No, there's no grader yet. I'm working on the grader. I don't know about tonight because I might just crash after lecture. But tomorrow I'll be working on the grader. And by the time you're done, these AI, they'll hunt the closest player. So you can just kind of sit in the corner down here if you want and watch the AI fight each other. Or you can join the fray, go out there and try to fight the AI. I'm going to try to hit one of these things. It's easy when you can just fire. And there's things, if you want to edit this game, if you want to add some more features to it, like not allowing this machine gun behavior. Oops. Oh my goodness, I can't hit the right buttons. And improve the game to be more compelling and more interesting to play. Having a win condition. I don't have any win condition. It's you just play forever. Then knock yourself out. Have fun. I would have liked to build the game out more, but I had to get this assignment out because it's already Wednesday. Yeah, I gotta get some rest. It's definitely sleepy time soon. So the Enemy AI, I think there was one more thing I wanted to talk about before. Just before lecture, I posted on Piazza, but in case you didn't see it, the lab results from last week are posted. So your LO3 read and explain are posted just in time so you know if you have to go to lab tomorrow or not. The results were pretty well. We're looking pretty good. A lot of you don't have to go to lab. I will say there were some complaints I even had about the concurrency questions that I had on the interview and quiz that the TAs asked you on the interviews and that Q3 on the quiz. When I graded those, I took that into consideration that I did rip through this content very quickly. I had this intent the whole time, and this is what I was planning to do. So if you did really well on everything and the only thing you got that you slipped up on was the concurrency and the WebSocket and not web actors, the actor stuff. If that's the only thing you did, incorrectly, I was very lenient with that because it's one, very rushed, and two, you didn't really have much time to study. Like I introduced WebSockets, and then the next day I have the TA asking you a question about WebSockets. Is that really fair? Maybe there could be an argument that that's fair. I don't know. I don't think it's super fair. Actors, you saw Monday, and then I gave you a program that uses actors on Thursday. I don't know how fair that is. Plus, I want to downplay the concurrency aspect of this course anyway. I already squished it down to a week. But if you got like the recursion and immutability stuff wrong, is there a week missing here? Oh, because I'm seeing green. If you got the immutability, recursion, and first order function stuff wrong, well, now we're talking about you better take the makeup. You got to take the makeup there. Concurrency, I was very lenient with. My brain is wrecked at LT4. LT4 is tough. LT4s were, I think, where the bulk of the difficulty for a genetic algorithm is. It's a lot of LT4. Once you get LT4, though, LT5 and 6 are pretty much downhill. You're pretty much coasting after that. Until you get to his AO1 harder than LT4. Yes, 1,000 times yes. If you want to get AO1, that's a huge jump up. If you want to get AO2, that's a huge jump up from AO1. The AOs are tough on this one. I will say I don't think the AOs are nearly as difficult on Project 4, on Enemy AI. I definitely toned down the application objectives. Not to say they're objectively easy, but I don't think they're as hard as the ones on Project 3. I don't think they're even close to that hard. So if that factors into your time management, factor it in. Okay. Any questions on any of this? Let me catch up on chat a little in case there's something I missed here. Sleepy time, yeah. Maybe we'll just take naps today. Can we just take a nap today and then I'll cover these slides on Friday? and then not do examples. Oh. Where's LO for range and difficulty between the other LOs? In between 1 and... I'd say 2 and 3 are about the same. 1 is easier. LO4, I think, is in between 1 and 2 and 3. I think it's a little bit easier than the other ones. And you can see that I communicate that a little covertly in the document, where I say 20 hours. The last 2 assignments were 25. And I think the first one I had 15 on. So I communicate that through the... Oh, I did say 20 on Pale Blue Dot. Pale Blue Dot's not 20. Pale Blue Dot's less than that. So I do communicate that through those. You can do that and do the example in a separate video. Oh, take a nap right now and then do the examples in a separate video. Yeah, I could. Or just stay late on Friday and do a bunch of examples. But, does the normal list work like linked list? Why are we using a separate linked list node class? So you get practice. So the Scala list class hides all the details. Like you can use that for days. You've used that the entire semester without really caring that it's a linked list. With the linked list node, you have to be aware that it's a linked list because you have to traverse it yourself. You don't have all the nice methods for a list to be able to work with that. Mainly, you can't just use a for each loop with my linked list node because I don't have an iterator. So you can't just say for node in linked list node class and iterate over the whole list. So you're actually forced to get into the structure and understand. What I want is for you to gain a feel for what a linked list actually is by working with that in the first 3 lecture objectives. Strictly educational purposes. Yeah, Rin just teach lecture. All right, let's get into some slides. Today's slides aren't too crazy anyway. And I'll be honest with you. I finished the assignment. I designed the whole thing. I wanted to get a stack and queue question in there, and I just couldn't find a way to jam one in. It would have been very forced if I did. So there's nothing on the project for stack and queue. So these will be confined to interview and or quiz questions, if they show up at all. Maybe it could be a good quiz question. I don't know. Would that be? Would I have the linked list question on the quiz? The quiz writes itself, by the way, for this learning objective. You'll have 3 questions: a linked list question, a tree question, and a graph question. Do I want the linked list question to be stack and queue? I don't know. I think I'd want just a regular linked list example. First test, we talked about this. We went through the project. And personally, I don't really like stack and queues. I'll talk about them because they're such a fundamental CS topic. And for lack of any other reason, you'll probably get asked about stack and queues on interviews and stuff. But stacks and queues are just linked lists. It's an application of linked lists. What I care about is your understanding of linked lists. If you understand linked lists, you can transfer all that knowledge to stack and queue without even me lecturing on it. So I'm only using this as a means, just like we talked about sorting a few weeks ago. I'm using stack and queue as a means to talk more about linked lists. Okay, so stacks and queues, these are very specialized data structures. These are data structures with restricted operations, and right away, this is the reason why I don't really like stacks and queues. Stacks and queues are built upon lists, linked lists specifically, except they restrict some of the functionality of a linked list. So if you have a stack, you have a linked list, but you're not allowed to use all of the features of a linked list. You're only allowed to use the stack features of that list. So from a programming perspective, that's kind of pointless. Why take functionality away from us and not let us use it? From a theoretical aspect, these are more important data structures because just when you say stack or queue, other developers, other computer scientists know what you're talking about. They understand what you mean when you say those words in conversation. Like we talk about the stack, the memory stack. Since we call it a stack, you understand what we mean. And what we mean is a last in, first out structure, data structure. Like that's what we mean. But we're really just working with linked lists, and those linked lists are restricted. Scala does have a stack and queue classes, stack and queue. They exist in the library, so you can say stack queue wherever you would say list and get the stack and queue, which are linked lists without all of the functionality of a linked list. And one of my favorite annotations and documentation ever is the Scala stack class. Even has an annotation right in it that says, I'll paraphrase, but it basically says, why are you even looking at a stack? Just use a linked list, dude. It's more feature rich than a stack. This is just a linked list with some of the features removed. And it's literally a stack in Scala is just a linked list with some of the features removed. Like, why do that to yourself? Why shoot yourself in the foot? All right, so with that, let's talk about what these actually are. A stack, it's a last in, first out data structure. If you ever hear someone say LIFO in their a computer scientist, computer science student, software engineer, anything, this is what they're referring to: a last in, first out data structure. We can think of this as a physical stack. Whatever the last thing we added to the stack is, that's the first thing that we have to remove if we want to access this stack. We can only access the top element of a stack. Just like the memory stack, this mirrors that. The memory stack, we can only access the top stack frame on the stack. We can't go digging through the stack and find the lower stack frames, the other stack frames. We can only access the last frame that was added to the stack. Same is true in general for the general stack data structure. Is the last element that was added to the stack is the only one that we can access. That's what a stack is. One slide. Are we done? No, we're not done. So the stack methods, whenever we talk about a stack, there are two primary methods in any stack anywhere in the world of computer science or software engineering. They're going to be called this. I say that, but as I say it, I'm like, there's probably some language that has to be different and calls them something different. But push and pop. You push to the top of a stack, that's adding an element to the top of the stack, and you pop from the stack, that removes the top element from the stack. Some languages and some implementations will have a third method called top or peek, which will return the top element, what will let you get a reference to the top element of the stack without actually removing it, where pop removes the top element and also returns a reference to it. So some implementations you'll have a third method that'll peek. I think C++'s implementation, it's likely changed since the last time I touched C++, but it has push, pop, which only removes the top element without returning it, and then either peek or top, I forget what one it's called, but that'll return the top element without removing it. So to do anything with the stack, you have to call top and pop to be able to work with it. I don't know. It's a tangent, I guess. But so let's build a stack class. We're going to build this around our linked list node. Again, this is for educational purposes. I'm showing you the structure of how we could build a stack. If you're ever wanting a stack in the real world, I would just use a Scala list, the built-in list. Or if you're crazy, you could actually use the Scala stack class that has a push and pop method. So our stack class that I'm creating that's in the repo that you can check out, you can take a look at, is going to have a linked list node. It's push, pop, peek for C++. Okay. Yeah, I was saying top, so peek instead of top in that example I just gave. I'm going to have a linked list node, which is going to represent the head of a linked list, or the first node in a linked list. I'm going to initialize that to null, so I'm going to start with an empty stack. And then whenever something is pushed, when an element is pushed to this stack, I'm going to add a new linked list node with that element and a reference to the previous top of the stack. So I'm effectively prepending the element A to this stack. Whenever I'm popping from the stack, I'm going to take the value of the head of this list, or the top of the stack. I'm going to return that, and I'm also going to remove that element from the stack by updating this .top to this .top .next. So I'm going to now refer to, top is now referring to the second element in this stack, effectively removing the top element from this stack. And that's our stack class. That's our implementation of push and pop. Add to the top of the stack, pop from the top of the stack. If we want to use this, we're going to create a new stack. Say I want a stack of ints. I'm going to push 3, push 7, push 2, push -5. So my stack here is 3 on the bottom, then 7, then 2, then -5 if we're thinking of this visually. When I call pop, I want to return the element and also remove it from the stack. So this is going to return -5. Oh. This is going to return -5. Yeah, it returns A. This is going to return -5 and also remove it from the stack. So after pop is called, my stack is 3, 7, 2. Here's my favorite annotation, my favorite deprecation warning. Why are you using this? This is silly to even use this. But Scala does have a built-in stack. You can use it. It has the same code. It would be the same code here. If this was importing Scala's stack instead of my stack, it's the same thing. Push and pop are behaving the same way. But there's this annotation. Stack is an inelegant and potentially poorly performing wrapper around a list. Use list instead. Like, what the hell are you doing? Why are you even using this stack class? So if you're ever needing a stack, if you're like, man, I need a last in, first out data structure in my code, just use a list. Like that's my advice. Why are you restricting yourself with the stack class? And I'm happy that the Scala developers support my position on that. So just use a list. A stack's built on a linked list. Just use a linked list, man. So create your stack as a linked list. Prepend to push to the stack. So pushing is the same as prepend. So let's just use prepend. So let's use prepend. We're going to prepend 3, prepend 7, prepend 2, and prepend -5. So our linked list is -5, 2, 7, 3. Or if we want to visualize it as a stack, it's 3, 7, 2, -5. If we want to access the first element, that's stack.head, just the method of a list to access the first element. And then to actually pop that element, we're going to set stack equal to stack.tail, which tail is the same as next. Tail, the way we use next for linked lists, Scala uses tail for that. They just name it tail instead of next. So we're going to set stack, this reference to a linked list node on the stack, on the heap, the memory heap, but the data structure stack. But this variable named stack is on the memory stack, and it's representing a stack data structure. Man, that does get confusing. So this variable, we're going to update that to a reference to the second element, the second node in this linked list. So we've effectively removed the -5, this element, which means we've effectively popped from the stack. So let's visualize this a little more using the representation we saw in previous lectures. And this is where a lot of stuff should come together here that we've talked about throughout the course. So I've mentioned many times that whenever you add to a list, you're creating a brand new list. And we saw on Monday that's a little bit misleading, because we're not creating a brand new list. We're creating a new linked list node, and that node's next refers to the old head of the other list. So this rectangle here, which is the state of stack is referring to this node right here at this point in the code. And when we want to prepend 5 to it, we're not actually destroying the stack or copying it or creating a brand new list. When we prepend to a linked list, what we are doing is creating a brand new linked list node and having it refer to the head of that list. So we did create a new linked list node, and now stack refers to this node. But everything we had in the old list is identical to what it was before we prepended -5. This is an important aspect of linked lists. This is why, if you recall, I've said a few times in lecture, prepend is much, much more efficient than append. We're going to see append. We'll talk about that when we talk about queues in a second. But prepend is a very efficient operation because every time we prepend, the old list does not change at all. So this does return a reference to a new list containing all the elements of the old list with -5 prepended because list in Scala, the Scala list is immutable. But it doesn't have to copy all of the elements of the stack of the list. It's a very efficient operator to prepend because we just create a new linked list node, not asking the OS for very much more memory, just enough memory to store an int and a reference in this case, and then just have next refer to the old list. Return a reference to this. This list doesn't even know that this new node is referring to it. This list, when we were just 2 elements, doesn't even know that this node is referring to it. This list with just 1 element doesn't even know that this list is referring to it. So we do have 4, what we used to think of as lists on the stack, but now we can see that we have 4 linked list nodes on the stack, and they're all referring to the next node in the ultimate linked list. So prepend, this is why it's a very efficient operator, because we create a new node and then just refer to the place in memory of the old list. Same with removing. If we want to remove an element, I did drop 1 here. I'm mixing things together. I did tail here and drop 1 here. Those do the same thing. They're going to update. They're going to return a reference to the second element of the linked list. So when we want to remove an element, we just refer to this node instead of this node, and we actually don't change anything on the heap when we update that. How would you write this as a stack and heap? Oh, in memory. So this is the heap, and then the stack is just this variable stack referring to the first element. So stack here refers to this object on the heap. Stack here, after we prepend 7, stack now refers to this object on the heap. Here, after this line, stack refers to this object on the heap. And then after this line, stack refers to this object on the heap. And then we're going to say stack equals to stack dot drop 1, which is the same as stack dot tail, which is the same as a reference to next in our terminology. Next. So now after this line is executed, stack is a variable on the stack that has a reference to this object on the heap. So this is the heap space. I didn't label it stack and heap like I've done in the past. But stack, this variable is on the stack. Element is on the stack. And then stack stores a reference to one of these linked list nodes that are on the heap. So append needs to reach the tail of the list first and then add a node to the tail. Yeah, and it's even worse than that. So let's talk about it. It's just saying what I've said earlier. All right, so now let's talk about queue, and we'll talk about append when we talk about a queue. So a queue, similar to a stack, except very one key difference. It's a first in, first out data structure, and it mimics a queue like you see, I don't know, anywhere, at the grocery store, at an amusement park, at a bank, anywhere, where you have to queue up. You're going to wait in line, and then when it's your turn, or office hours, I didn't even say the obvious one, office hours. The office hour queue, whoever's the first one to arrive is the first one to exit the queue. The first one in is going to be the first one out. And if you're the last one in, you're going to be the last one out. You got to go through everybody else in front of you, has to be seen, and then you get to the front. So this is a queue. Elements can only be added to the back of the queue, and elements can only be removed from the front of the queue. So we have 2 methods. Just like the stack, we have 2 methods. Enqueue, or enqueue, I'll pronounce it different ways, different times. enqueue is going to add an element to the end of the queue, and dequeue is going to remove the first element from the queue. We can write a queue class similar to the way we did a stack, but we have a little bit more work we have to do. We have to have a reference to the front and back of this list. Since we have to work on both ends, we have to have two references in our queue. One to be able to remove elements from the front, and one to be able to add elements from the back. We're going to initialize them both to null. And we have a little extra logic to do in our methods as well. If we enqueue to an empty queue, we're going to create a new linked list node and set that equal to both the front and the back of the queue. Both front and back will refer to the same linked list node on the heap, which is what we want. We're careful with our references. We're careful with our stack and heap. We want these referring to the same object on the heap, and we want there to only be one linked list node in existence here. We have a queue of size 1. Front and back refer to the same object on the heap. If the queue is not empty, we're going to add that new element to the back. We're going to create a new linked list node that refers to null, and then the last element in the queue, we're going to have that refer to we're going to change back to refer to this new element that we created, and then have the old back refer to the new element that we created. So we've appended to the end of a linked list. Now this is actually efficient because our linked list node represents a mutable linked list. So this actually is efficient. We get great runtime, great operations with this. We actually get O of 1 runtime in all our two operations for a queue here. Dequeue, it's going to look at the front of the queue, return that. Looks just like pop for a stack. Same thing. We're going to get the value, return it, and update our reference to the next reference. Except we have one extra check. If front equals null, that means we've emptied out the whole queue. And we're going to set back also equal to null. So back isn't referring to a linked list node that is no longer in the queue. Our usage. This, we're going to have a queue of 3, 7, 2, -5. When we dequeue, that's going to return 3. That was the first element in, so it's the first element out. Scala has a queue. It actually is based on Scala's mutable list. Scala does not use its immutable linked list, its immutable list class for a queue, because if you use an immutable list for a queue, you're defeating the whole purpose of a queue. So, which I guess I forgot to mention up top, is the whole purpose of restricting the functionality for stacks and queues is to restrict you to only O of 1 time operations. So you're only allowing developers to call very efficient methods. There are no inefficient methods in a stack and a queue. So if this queue was built on an immutable list, it wouldn't be efficient, and there would be no point in having that restriction. Like just use a list. I say just use a list anyway and just be responsible about it and think about your data structures. What does O of 1 mean again? It means no matter how large the data structure is, the runtime of all the operations is the same. They're always going to be very efficient. Like prepending to the beginning of a linked list, we create a node, set its next equal to the head of the node, and that's it. No matter how large that list could have 1 billion elements in it, that's going to take the same amount of time no matter what. Append, that is no longer the case if your list is immutable. So when we append to a queue, when we enqueue to a queue, we can do this in reverse. We could enqueue to the front and get rid of this problem, but then we'll have this problem when we dequeue. No matter what, with a queue, we have to work with both ends of the list. So whatever operation is happening at the end, this end of the list, you're going to have this problem, whether it's enqueuing or dequeuing. So if this list is immutable, meaning we have a list and we want to make a change to it, to make a change to an immutable object, we create a copy of that object with the change applied. We got around that with prepend by just returning a new linked list node that happens to refer to the head of the old list, and then we had a larger list without changing anything else in memory. When we append to the end of a list, we want to append to the end of this list, we actually have to make a change to the old list. We have to take this next value and update it to the new node that we just created to append the new element. So this list has to change. If this is immutable, you can't do that. So if this is an immutable list and you want to append to the end of the list, of the immutable list, you do have to make an entire copy of this whole list. You have to copy the whole thing. What else are you going to do? How else are you going to do it? You got to make a copy of this list and copy every element of this list if you want to append to the end. So you also have the problem that was mentioned in chat where to append to the end, you only have a reference to the head node. So first you have to traverse the entire list. It's only 3 elements here, not too big of a deal. That's where 1,000,000 elements, that's a big deal. You got to traverse the whole list, get to the last node, create the new node, update next, which you can't do. So you have to go, oh crap, I have to make a change to this immutable object. So you have to go through the entire list, copy the whole thing, add that new element, have the last element referred to the new element, and then return a reference to the head of the new list that you just created, that entire copy of this whole list. Append with an immutable list is far more expensive, takes far more time, O of n space and O of n time, than prepend. Prepend just constant time, very fast, very efficient, because of the way a linked list is stored in memory. The way we have these, just all the implications of this. Next, referring to the next node, and the fact that a list, that Scala's list is immutable anyway. Our immutable list doesn't quite have this problem. We still have the problem of we only have a reference to the head, so we have to traverse the whole list and then append that element. But with an immutable list, this problem is massive. So if we want immutability, which we generally do in programming, especially when it comes to concurrency, which you haven't really felt yet, but we do want immutability in most cases, especially concurrent and distributed systems. We want to avoid appending to the end of a list. All right, we're not going to get through that whole stack example. I wonder, I might ad-lib this a little bit. Yeah, let's go for this. Examples. Oh, I was writing last time. Oh, you know what? I do have this set up. All right, let me catch up with my example quick. This lecture went by fast. Yeah, I spent a lot of time at the beginning talking about the project. So here I'm creating a random list of n elements. They're just random values, and I'm prepending to the list. I don't think I need any of this. Oh, I think I had an issue with this before. I think Scala, the compiler, does a lot for us. So I think I ran into trouble here. But hey, let's just run this, and then I have a method to time it. Why is time function wanting to return some? This should work right here. So I'm creating a random list with 100,000 elements, and it took 1/3 of a second. Let's do the same thing, but let's append instead of prepend. I don't use append very much, so I forget what the syntax even is. I think it's colon plus. I just avoid appending whenever I can. So the difference between append and prepend, we just created a list of 100,000 elements. It took a fraction of a second. All I did was change this to append instead of prepend, And I don't even remember how long this is going to take, but it's been running for a while now already. This is something that you do have to be aware of. If you're using Scala's list, and this is something you'll, of course, talk about a lot in 250 next semester. If you're using Scala's list or any immutable list or any immutable data structure in general, you have to make sure you're not copying the entire data structure on every operation, where you're going to have horrible runtimes. Like if you're designing a website, you have a lot of data and you're appending to a list, and the user has to wait 46.7 seconds every time the page has to reload, you don't have many customers. You don't have many users at that point. But all that you did was append instead of prepend. If you append, and even if you want the ordering of prepend, just do list.reverse at the end. Just reverse the list. Reverse is a pretty quick operation. I mean, it's not, but you're only calling it once, so it's fine. Just reverse it if you want that ordering. Don't append just to get the right ordering. 0.2 seconds. Hell, let's go to 1,000,000. Let's create a list of 1,000,000 elements. Let's create 10,000,000. $10,000,000's taken a little bit, but 2.2 seconds to create 10,000,000. I'm not going to wait long enough to figure out how long it would take to do 10,000,000 using append. It would take friggin' forever. We could probably even go down to like 1,000 with append, and we'll feel the pain. List append. Okay, 1,000 ain't too bad. But once you get up to in the 10,000 range, that's where you start feeling your pain. 0.7 seconds. Nah, not terrible, I guess. And then 100,000, that was what we ran the first time, right? That one we know takes a long time. 50,000. Int.value. That could be, I believe this is the same as 2int. Not sure why I did int.value there. Okay, 10 seconds, 11 seconds with 50,000. Once you start getting into that tens of thousands range, so this is going to be an n squared operation. The random list is going to be n squared. For every n, for all n, each n elements, it's doing n work. So we have an n squared. This is going to be an O of n operation. So we have an O of n squared. When you have O of n squared, typically it's when you reach the tens of thousands that you're not getting away with that anymore. You can't use an O of n squared operation anymore. You gotta flatten out your loops. You gotta be careful about your runtime. That's where the practicality is gonna hit you. You gotta be getting to n log n at worst at that point.